Hey guys, welcome back to another paper. So here we're going to do a complete breakthrough and a walkthrough of the M1 June 2017 paper. So as always, I'm going to go straight into this and yeah, let's see how it goes. So let's look at firstly number 1. Okay, so free forces 15I plus J newtons, 5QI minus PJ newtons and so on, where P and Q are constants, act on a particle. Now, given that the particle is in equilibrium, in other words, this means that the resultant forces are equal to 0, find the value of P and value Q. So, okay, all this means that we need to add all these forces, let's call it F1, F2, F3, and they all sum up to 0. So, the key idea here is to realize that we can work in I's and J's. So, if we're going to sum up each force, we can say that if we're working in I's, then we can say that 15 plus 5Q minus 3P must result to 0I, correct? And as for the J's, we can say that first one is literally 1J, so 1 minus P minus QJ must result to 0. So these are the two equations. So in fact, these are simultaneous equations. Now to make our life super easy, well, let's just do what we do for simultaneous equations and just find a common coefficient. So let's multiply the second equation by 5 so we can eliminate the, it's actually a different order. Let's multiply the second equation by 3 actually, so we can eliminate the 3p. So doing that, we should have 3 here, 3p and 3q. Now, what I could do here, I got minus 3p minus 3p, I could subtract these completely. So you could do it various ways. You could use simultaneous equations or, yeah, up to you. So let's have a look. So we've got 15 take away 3, we should get 12. Now 5q minus 3q will give us plus 8q. And of course, minus 3p take away minus 3p is nothing. And 0 take away 0 is 0. Now just solving this one, subtracting 12 and dividing by 8, so it'll be minus 12 over 8. This should simply reduce to, I mean, you could always use a calculator like I do, because honestly, it's easier. We should get simply minus 1.5. And lastly, now to find P, well, I would just go back and use the second equation. So we initially had 1 minus P minus Q equals 0. So effectively, plussing P across, P equals 1 minus Q. So it'll be 1 minus 1.5, and you should get 2.5. So P would be 2.5. That's it. All done. Let's move on. Okay, question 2. So we have two particles P and Q, and they have masses 2m and 3m respectively. So they are moving towards each other in opposite directions on a smooth horizontal plane where they collide directly. Now apparently, before their collision, the speed of P is 4u and the speed of Q is 3u. Okay. As a result of the collision, Q has its direction of motion reversed and is moving with speed P. Speed u. So what I would do firstly is I would actually draw this out. Okay, so firstly, let's imagine this is P and this is Q, and they're both moving, they both have masses 2m and 3m. They're moving towards each other in opposite directions. So again, this was P and Q, so this is moving towards Q and this is moving towards P, and they have speed 4u and 3u respectively. Okay, that's from here. Now, apparently, after they collide, Q has its direction of motion reversed and is moving speed u. So this means Q is now going here. So we can call this speed u. Now, they want us to find the speed of P here. So what we could say, just to make it easy, I always work with the direction of motion. I'm going to make direction of motion here. So this is our direction of motion. So this means we can call this one, let's just call it V. Okay. And now, the way I would resolve this is I would use the fact that the sum of the total moments, or momentum actually, must equal to 0. So we can use this unique formula that I use. I say that the first mass times the impulse. So basically, this is just the impulse equation. It will be V1 minus U1 plus the sum of the other mass times the difference in the speed, so V2 minus U2, must total 0. There is other formulas that you're familiar with, but I generally use this one because it reminds me of the sum of the impulses. They must eventually hit to make 0 because that's the whole point of it. Now, all you do is literally just plug in and see, and literally make an expression for the speed of p. So what do we know? So because we're working in this direction, working towards the direction of motion, which is this way, we can plug everything in. So the first mass will be firstly 2m. Now this, because we're working this way, we can say that the final speed is v minus the initial speed of 4u. Now this is all p done. And as for q, we have a mass of 3m. And we can say that the final speed was u minus the initial speed, which is, in this case, because it's the opposite direction, it will be minus 3u. So it will be plus 3u. Okay, not bad. Now, all you do is just tidy up. So let's have a look. So firstly, we can cancel all the m's out because, well, if you divide m across, it'll be gone. And expanding the bracket, we should have now 2v minus 8u plus 3u plus 9u equals 0. And now finally, let's just collect like terms here. So we got 2v, we keep there. Where was my pen? And we got minus 8. So we got 3u plus 9u is 12. 12 take away 8 is 4, so it'll be plus 4u equals 0. And finally, solving this for v, we should get v equals minus 2u, and hence, because it's negative, the speed is negative here, we can say that the direction of motion has been reversed. So for part B, state whether or not direction of motion has been reversed. Yes, it's been reversed. Okay, so if it's positive, it goes in the same direction. If it's negative, it flips. So the arrow should really be pointing left with a speed of 2u, or right with a speed of negative 2u. Now finally, an easy part. Find the magnitude of the impulse exerted on P by Q in a collision. Well, the reason why I like this formula as well is because once you present it like this entire formula is actually an impulse. They're both impulses. Because if you imagine a dotted line across here, the general idea is that the impulse acts like a reaction against the collision. So really, this entire formula is equal to I, both of them. Okay, so whatever result you get this one, then you practically found your impulse. So let's do it. Let's just take, I don't know, so in this case it says exerted on P by Q. They should both give you the same result because I plus minus I should give you 0. So let's just take the first one, yeah? So let's see. So we've got V, which is now minus 2u. So minus 2u minus 4u should give us, let's have a look. So copying this one down here, we should get a mass of, oh my god, what am I doing? Of 2m. Is it 2m? So 2m times v, which is minus 2u minus 4u. So you can get a negative value because this is equal to, this is opposite direction of motion, right? So this speed equals to negative I. The other one would equal to positive I, by the way. So solving this one, you should get, let's see, minus 6u here. So times it by 2, you should get minus 12mu equals negative I. So the impulse must be 12mu. Try for the right hand side. You should get the same thing. Why? Because let's double check. U plus 3 is 4u times 3 is 12. So again, this one is also 12mu. Question 3. Okay, let's go. So according to this question, it says that a plank AB has length 6 meters and mass 30 kg. Now, according to this one, the point C is on the plank with CB equals 2 meters. Okay, before we carry on, let's go ahead and draw this plank here. So let's assume the plank looks a bit like this. So just a long one. So we'll call this A and B. We know that it's 6 meters long. And what do we know? Do we know it's uniform? Yes, the plank is modeled as a uniform rod. So it is. This means that the center mass is bang in the middle. And it's, of course, a mass of 30 kg, so 30 g, and a distance of 3 meters away from A and B. Now, we also know there's another thing at point C. So point C is 2 meters away from B, so it's somewhere around here. And let's call this C. And 2 meters away from B, so it's practically 4 meters away from A. The idea is that I'm always going to take moments around A because it's easier. Now the plank rests in equilibrium in a horizontal position on the supports A and C. So we've got supports there, meaning there's some sort of reaction going on. Now before I carry this on, I want to see if the reactions have any values. And yes, if you look at this line here, the plank remains horizontal and in equilibrium with the magnitude of the reaction at C 5 times the magnitude of reaction A. So if the magnitude of A was say R, then C would be 5 times R. Okay, that's cool. Now let's carry on where we left off. So 2 people, each of mass 75, stand on the plank. One person stands at point P, where AP is X, and the other person stands at Q, where AQ is 2X. So let's just say, I don't know, one guy is over here, yeah? So let me just change the color of this. So we got one guy X meters away, and he weighs 75 Gs. And another one, say, let's say over there. Again, 75 G, and the distance here is 2X. And now we can just resolve vertically, yeah, so resolve to find the value R and then take moments about A to find pretty much X. So let's do that. So firstly, resolving upwards, we can say that we got R plus 5R, which is 6R. And now resolving downwards, we got 75 plus 75 plus 30, which is 180 Gs. This means that R must be equal to, divide by 6, and you should get 30 Gs. Alright, so that's one bit done. Now the easy bit, well, that's the easy bit. Now the next easy bit is to take moments about A. The key idea of why we take about A is that you can instantly say that the sum of all the moments going upwards is equal to the moments going downwards. And trust me, this is the easiest way if you want to just solve it without making as many mistakes, or to reduce the error, yeah? So, and another thing is, if you resolve A, we can cancel out this point, this entire force upwards, because it's at the same point, so the distance is 0, since R times 0 is 0. Now let's do this. So first things first, going to 5R, what is it? It's going to be 4 meters across, so 4 times 5R will give us 20R, and well, R is 30, so 20 times 30 is 600, so it'll be 600 Gs. Now, as for the downwards, it's going to be first things first, so X, where's my mouse? X times, what's this, 75, which will be 75 Gx, plus, if you go up to 30 G, it will be 3 times 30, so 90 G. And lastly, if you go all the way up to 75 G, it will be 2X times that, so it will be 150 Gx's. And that's cool. Now, you just tidy up and just solve for X. So, oh yeah, and you can cancel the G's as well. So every single G's can vanish. Bang, bang, bang. So yeah, subtracting 90, you get 510. Collect like term 75 and 150x gives you 225 x's. And finally, x must equal 510 over 225. And just smash it in your calculator. So 510 over 225. I got 34 over 15. And just to know what that looks like, 34 over 15, that's about 2.26 recurring. There's 6 parts recurring, yep. Meters. So x is actually, so I made a fair assumption. X is just before the 30G. Okay, now this one's one of those typical state that questions. So let's have a look at this wordy problem. So state 2 ways in which you have used the assumptions made in modeling the plank as a uniform rod. Well, 2 words, uniform and rod. So as a rod, we can say that this rod is straight, as you can see, or not, my one's kind of bendy. But usually you gotta say that the rod does not bend, it's straight, it's rigid. So that's one of the major things. The second thing is the fact that it's uniform. This implies that the midpoint is actually in the center. So this is quite clear. Looking at the mark scheme, I'm going to open up as well actually, so to see more options. It states that uniform mass is or acts at a midpoint of plank. So that's quite clear. I'll take this definition. Or the center of mass is at the middle of a plank. So something that implies that uniform means, in terms of rods, that the center of the mass is bang in the center or in the midpoint. As for the rod, it just means that it does not bend, must be straight, because of course if it's bent, then the center mass could be elsewhere. is inflexible, is rigid. I would use pretty much that the rod is straight and does not bend. Probably rigid too. And yeah, that's really it. So let's move on to the next one. So it says that a particle P of mass 5 kg is held at rest in equilibrium on a rough inclined plane by a horizontal force of 10. So here we go, and here is a rough inclined plane. So just to make it clear, when it's rough, this means there must be some sort of friction happening towards the ground. So we can call this coefficient friction mu. Okay, that is the value between 0 and 1, relating how much friction there is. Now, what do we know? The plane is inclined to horizontal at an angle of alpha, where tan alpha is 3/4. So we need to relate some triangle using the usual trigonometry, where we got alpha here, and we got 3/4, so opposite over adjacent equals tan. And using Pythagoras, you'll eventually get 5 here as well. So we can just work with this in a second. Now the line of action of the force lies in the vertical plane containing P, and the line of greatest slope of the plane. Okay, cool. Now the coefficient of friction between P and the plane is mu. Given that P is on the point of sliding down the plane, so if it's sliding down, meaning there's some friction behind it this way. So this is the friction value of F, where we can say that at limiting equilibrium, F is pretty much less than or equal mu r. That's how we write it. Or, just to make our life easy, for the sake of question, the maximum value F is equal to mu times r. So the coefficient of friction times the reaction of the plane, where the reaction is always perpendicular to the plane itself. Okay? And one more thing that we need to add. Yes, we need to add the particle P of mass 5 kg. So this is going vertically downwards, and it's 5g. So this is completely down, yeah? Okay, and here we go. So now all we need to do is pretty much label our angles. This will make resolving this so much easier. So I always follow the direction of, let's say, the reaction itself. So if I was to extend this line, I could say that the weight is at an angle of alpha. Okay? And if we're looking, well, the force is completely perpendicular, so that's good. Now the push, the 10 newtons, if we just extend the line, because if you extend the force, it's the same force. We can see that it's perfectly, horizontal. So just making an incline, we can say that this is at an angle. If we just tilt ahead and follow this line here, this is at an angle of 90 minus alpha. Because if you think about it, this is perfectly perpendicular to each other. Alpha plus 90 minus alpha will give us a nice clean right angle. So towards this line, the south line, it will be 90 minus alpha. And is that it? Yeah, I think that's really it. So how about we go ahead and start resolving now. So firstly, resolving towards the reaction itself, we should get R, and that's the only upward force. Now the downward forces, we have 5g cos alpha, and this one 10 newtons. All right, 10 here. It will be 10 cos 90 minus alpha. So it'll be, let's do it here. So it'll be minus 5g cos alpha. So the reason why I'm using cos is that this is the method I use. Every time I'm following towards the downward force, I use cos. That's why I always aim towards the downward one. And this would be minus 10 cos 90 minus alpha. And all of this, I believe, should equal 0. One thing to note now is that when you have cos 90 minus alpha, there's a cool property, and you should just memorize this, is that 90 minus alpha is identical to sine alpha. Why? Because if you think of the sine and cosine graphs, 90 and cos and sine are just 90 degrees apart. So it makes sense that the difference between 90 will give this other version, sine. And we know these values, cos and sine, because we have the triangle, the trigonometric triangle, the right angle one. So looking at cos is simply adjacent over the hypotenuse. So the adjacent here would be 4 and hypotenuse is 5. So this value here is 4/5. You could find alpha, but this is more accurate. And sine would just be the opposite over the hypotenuse. So it would be 3/5. That's an easy way to calculate it. So that's done. You probably already know this, but just to be sure. So solving this completely, we can say now that R equals, so throwing everything to the right side and simplifying this, you got 5g times 4/5 is just 4g, so it'll be 4g here, plus, and 10 times 3/5, so cancel the 5s, you get 2, and you should get 6, so 4g plus 6. So that should total to 4 times 9.8 plus 6. Let me have a look. 10 times 3/5. And you should get 45.2 newtons. So that's the value of the reaction. Okay, not bad. Now let's go ahead and resolve towards F, yeah? So let's see what else we can also resolve towards F. And if we do that, what do we have? So we've got F perfectly done. Now let's find the angle behind it. So if we have to extend this dotted line, and let me change to blue. Extend towards the dotted line here. We can see that the angle here would be 90 minus alpha, because you can just complete this triangle here. This is 90 minus alpha. And what else do we have? That's the 5G line. Now the 10 newtons, we can just, is going towards the same direction as F. So that would be angle of alpha, which is the same as this angle here. And R is perpendicular, so we don't include that. And that's it. So we've got F and 10, which are positive, and we've got 5G, which is on the negative side. So we can say F plus 10 cos alpha. So F plus 10 cos alpha. And on the negative side, we're going to have minus 5G cos 90 minus alpha. So 5G, and 90 minus alpha is just sine alpha, equals 0. Alright, not bad. Now just make F the subject here. So we're going to have 5G sine alpha minus 10 cos alpha. So just throw everything on the right side. And record that F is this UR. And we know what R is 45.2. So it'll be 45.2 times mu equals all of these. So 5G, so we can go ahead and just smash this in the calculator. And I got 21.4 newtons. And now finally just dividing 45.2 across, and you should get, yep, 0.473 for the coefficient of friction. And that's it, guys. This is done. Question 5. Now, most people found this a bit tricky, mainly because of the involved mention of the word thrust in the rod. Now, just to be clear, thrust is the opposite of tension. Tension is basically when it's pulled away, so we follow the direction of the string. Whereas thrust in the rod is when the rod itself compresses. And to understand the visual demonstration, I'm going to post a screen of an information from the standard M1 textbook that you probably get in school. For example, I'm just going to look at this information here. It says if an object is being pushed along using a light rod, the force acting on the object is called the thrust or compression in the rod. So have a look carefully. If it's acting towards it, here is the thrust. Now let's get back to the exercise. Now I think we can do this. Okay, here we go. So here is more space so we can actually solve this. So first things first, redraw the system here. So we should have P and Q down here. P and Q. So, and just to put the weights back in, we know that at particle P there is a mass of 0.5 kg, so 0.5 g, and at Q there is a mass of 0.75 kilograms, so 0.75 g. We also know that the system is accelerated vertically upwards, so let's do the acceleration sign pointing upwards. And there's a force of 50 newtons applied, a vertical force of 50 newtons applied at Q, sorry. So it would be here, 50 newtons. And of course, we just always work in newtons, yeah? Now, we need to find the thrust in a rod. And just in case we forgot, we previously mentioned that the thrust kind of works like a compression or a push. So it's like a push at Q, meaning that there is going to be some form of compression involved at P. So we could say that there's a thrust like here, like pushing it, will be thrust of T here, and another thrust, a compression resulting at T here as well. And that's it. This is how the system should kind of look like. Now the question is, we have to now resolve it to get the definite answer. Let's go ahead and resolve firstly at P, yeah? So I'm going to use red. So I'm going to work in this top left corner. So resolving at P, we can say that resolving towards the direction of the acceleration, so upwards, we're going to have firstly, where there's no positive value, so it'll be minus 0.5 g minus t, and this is going to equal to mass times acceleration, so 0.5 times a. Now at Q, same thing applies. So Q's got two positive values. We've got 15 plus t, so you can say 15, now put plus t so it matches here, and the downward force would be minus 0.5 g. So it's probably best to just to match them, because the point is we're going to probably use simultaneous equations to find the values at a, then eventually t. And yeah, this is going to equal 0.75a. That's it, guys. So this is where we are right now. So now all we have to do is resolve this. So what I would do, firstly, I want to eliminate t. To do that, what we could do, we could just subtract these forces. Actually, no, we can add these forces, because minus t plus t cancels out and becomes 0. So let's go ahead and add these. So nothing at 15 is 15. Minus 0.5 grams g minus 0.75 g, so no grams, is 1.25 g's. It's a gravitational force, and this would be 0. Now, adding the two accelerations, you should get 1.25a. And finally, making a the subject, dividing 1.25 across, you should get exactly 2.2 meters per second square. And that's it. We've done acceleration. And finally, to find tension, well, pick any of these two and you should get a result. So I'm going to pick the first equation because it looks easy to work with. So we can say firstly, plusing 0.5 g across, we should have minus t equals 0.5a plus 0.5 g. Now notice how this value is actually negative. It does look quite weird, but this is going to give you 6 newtons. And technically, t itself will give you minus 6. But that's fine, because the way we're looking at it towards a negative thrust. And at the end of the day, the magnitude will always be positive. Because if we're pointing upwards, this should technically be negative, which makes sense. Either way, it doesn't make the case. So the final result would therefore be, the thrust would therefore be plus 6 newtons, because there has to be a positive value. And that's it, guys. I hope this helped, and let me know if you got any further suggestions to this question. I would like to hear it, but otherwise let's move on to the next one. Question 6. So this is one of the usual SUVAT style equations, so pretty straightforward this problem. So what does it say here? So a cyclist is moving along a straight horizontal road and passes a point A. 5 seconds later, at the instant when she is moving with speed 10 meters per second, she passes the point B. She moves with constant acceleration from A to B. So this seems pretty straightforward. So let's firstly just draw a straight line from A all the way to B. So something like this. And we know, according to this statement, and we know firstly it's a straight horizontal road, so it stays here. And she passes a point A. Now 5 seconds later, she literally gets to point B at the speed of 10 meters per second. So she's here right now with a speed of 10, and this is at time 5. So it takes 5 seconds from A to B to get there. And now we also know that she moves with constant accelerations throughout the whole journey. So the constant acceleration is here, A. Now we need to firstly, so given that AB is 40 meters, so given that the total distance AB is 40 meters, find the acceleration of the cyclist as she moves from A to B. Pretty straightforward, this one. So we just need to think, what SUVAT equations we have here, what is relatable? So first things first, we need to find what A is. We know the distance is 40, so S is 40. We also know the final speed at B is 10, and we also know the time taken was 5. So there is one equation, but it's always best to look at this together. So here are the list of SUVAT equations from Google I'm looking at. Now we need one that relates S, V, T, and A, and the one I can see straight from here. So ignore all the U ones. So ignore the first, second, third, fourth. So we need the last one. S equals VT minus half AT squared. So always write this down. I always personally write this down in an exam, all 5 equations, and just see what is missing, and I just don't choose that. Now back to the work. So it's going to be S equals VT minus half AT squared. Now literally just plug it all in. So we're going to get so far, so S will be 40 equals V times T. So 10 times 5 is 50 minus half of AT squared. So we want A. So half of T squared. So half of 5 squared is 12.5 A. And that's it. Now just rearrange to make A the subject. So A should be, so plus 12.5 across, subtract 40. So you should have something like 10 over 12.5 if you rearrange it correctly. And this should give you, yep, 0.8 meters per second squared. And yep, that should be the correct answer. Now let's move on to part B. So now we need to find the time it takes her to travel from A to the midpoint of AB. Now, first things first, we don't know what the speed of is at A, so we should of course try and evaluate this term here. So let's just call this one U for now. And before we get to the midpoint, which is literally bang out here, so that's 20 meters across, let's find out what the initial speed was using our original equation, yeah? In fact, you could actually use it with acceleration. So another relatable equation we could have used is the one we saw earlier, which was this one. So we could use S equals UT plus half AT squared. Since we already know what A is now because we solved it, we've got S and T already. S is 20 and T is 5 seconds. We can find U. So make U the subject. So I'm going to make U the subject here. So U equals S minus half AT squared over T. And doing this, you should get S is 40, so 40 minus half of 0.8 times T squared, 25 over 5. And you should get 6 meters per second. So that is the initial speed there. And now, lastly, now we got the initial speed. We can find out the new time it takes for it to get to the midpoint. So to get to the midpoint, it will take, it's 20 meters long, and we need to find exactly the time left is to get there. So we could use the initial speed. We could use the acceleration because it's constant, remember, throughout the whole journey. And we know S is 20. So now, in terms of equations to use, you got quite a few options, but I'm just going to go back and use the same equation here because why? We have the U, which is 6. We have S is 20. We have A, and we need T. So we need these 4 variables, and this one has it. So using the same equation, now we're gonna have S equals UT plus half AT squared, and the aim is to find the time, yeah? So let's just plug in everything we know. Remember, the distance to the midpoint is 20, yeah? So this means this equation becomes 20 equals U, which is 6, so it'll be 6T plus half T squared. So half of A was 0.8, so half of that is 0.4T squared. Now, this is the part where nobody likes to do. So here we need to use the quadratic formula. So let's just go ahead and make it look neat. So rewriting in the usual quadratic formula, it should be 0.4T squared plus 6T minus 20 equals 0. So I'm going to assume that you guys are pretty capable with the quadratic formula. So it's just going to be T equals minus B, so minus 6 plus minus the square root of B squared, so 6 squared is 36, minus 4 times A, which is 0.4 times minus 20, so that becomes a plus 20. And this is all over 2 times A, so 2 times 0.4. Now I need to quickly calculate this one, guys, so let's go ahead and do it. So minus 6 plus 36 times 0.4 times 20. Of course, always double check if I did it right too, yeah? Okay, so I got, the first result was 2.81, so 3 significant figures, or how many dp? Well, so 2.81 seconds, yep. So that's when I use a plus sign, and I'm guessing if I use a negative sign, well, it'll probably be wrong. Yep, you get a negative time. So that means the only solution will be 2.81 seconds. And that's it, guys. Hope this video helped, and let me know how you found this entire problem. It's quite a good one, actually. It's quite a nice worked example. So have a look at all of this and just, send me your thoughts. Anyway, speak soon, guys, and ciao. Two ships, P and Q, are moving with constant velocities. The velocity of P is 9I minus 2J. So let's just note that down. Whereas the velocity of Q is 4I plus 8J, and they're both measured in kilometers per hour. So make sure we definitely remember that for a later question. Anyway, as for this one, we just need to figure out how to calculate the directional motion of P, given your answer as a bearing. So what this really means, every time we're involved with directional motion, this is just simply looking at the directional vector, or in terms of mechanics, the velocity vector. Okay? So first things first, let's go ahead and plot this on a IJ graph. So just make a little XY looking axis. Now, this is telling us that it's moving east, 9 across is moving 9 across, but 2 down. So it should be something like here. Okay, so we pretty much can just draw a dotted line here. So, and we can just say that the direction of P is moved 9 across to the right and 2 down. And all we have to do is simply calculate the angle. Now, because we're working out the bearing, it's always from the north line, right? So we need to find out the total angle from the north line straight to theta. So basically, we're looking at a bearing of literally 90 degrees because of the right angle, 90 degrees plus the value of theta. And that's it. This should be the result we're looking for. Now, let's go ahead and calculate this right angle triangle, yeah? So just plotting over here just to make it easy looking. 9 and 2. And we put the angle here. We just need to just recall our SOHCAHTOA here. So just recalling that every time that the length opposite the angle is known as the opposite, and that the angle next and the length next to it is always known as the adjacent. The long side is always a hypotenuse, but we don't really need that because that's irrelevant. So the two things that's related to this one from SOHCAHTOA would be the TOA. Okay, guys, because TOA has opposite and adjacent, so it must be the tan one. So we can say instantly that the equation of interest would be tan of the angle theta equals opposite of adjacent, so 2/9. That's it. Now all you want to do is just tan inverse this. So make sure your calculator is always in degree mode, yeah? If you guys don't know the difference yet, so don't worry about degree or radians. But make sure it's in degree mode and then tan inverse the solution, and you should get 12.5. So theta is 12.5 degrees. And that's it, guys. That's literally how you do it. And now you just add 90 to it. So plus 90. And you should get a total bearing of 102.5 degrees. Voila. Now, common question is this. I mean, there's nothing about position vector, but usually, if you're given a position vector and velocity, why do we not use a position vector? Well, that's simply because a position vector is just simply a coordinate, and a coordinate has no angle or direction. It's just a single point. Whereas a velocity, like this, is a direction. This is telling us it's moving 9 blocks to the right and 2 down every single hour. So it's always moving like this. So it's always moving in this direction every single hour. So that's why we know there is a direction. And the nearest degree would simply just be 130 degrees. Okay guys, here we go, part B. So I've already taken some information that might be useful for this question. So I'll put down the velocities of P and Q because this is important to solve the rest of these problems. And according to the statement, well, let's have a read of this. So according to this one, when the time is 0, the position vector of P is given to be 9O plus 10J. So this is the initial position vector, right? Because we're at time 0. And as for Q, is I plus 4J. Now, at time t hours, the position vectors of P and Q are P and Q respectively. So let's find expressions for both. So one thing to know, this statement here at time t hours, this is basically telling us that the general position vector at time t, like in this format, so RT equals the initial position vector at time 0 plus the velocity times time. This will give you whatever point you're starting at plus that direction. This will give you the movement it will be at. That will be its exact position from the initial and the direction you're going at some time t. Okay, so all we have here, so basically to make sense of this one, to find P, we just plug in 9I plus 10J into R0 and the velocity in its respective velocity vector 9I minus 2J, and we just tidy up, and then we do the same thing for Q. So let's do this. So replacing RT with the letter P to make sense of it, R0 is going to be 9I plus 10J. So this is just basically if you know the formula or not. Plus, and then we're going to have the velocity vector of P is 9I minus 2J times T. And as for Q, same thing applies. Position vector, the initial position is I plus 4J plus, and its velocity is 4I plus 8J times T. There we go, straightforward. Now, part C, hence show that at time t hours, what do we have here? The going from Q to P is given by the following. Now, when it says go from Q to P, we literally just have to find the direction from these two vectors. just think of it like this. You got position vector of say q there and position vector of p, and that's where we're basically going to that direction. So to find this entire expression, this is simply the difference from p to q. You just do p take away q to get this. Now let's try that actually. Let's find the difference. So subtracting these vectors across, what do we get? So let's have a look. So we've got 9i minus I, so this will give us 8i. So let's write here. So let's call this, let's do this down here actually. So we have QP. So we're going to have 8i, good. 10 take away 4 is 6, so plus 6j. Now 9i, now in terms of t, 9it take away 4it will give us 5it. So plus 5it. Actually I should write 5ti. Makes more sense. And then minus 2 take away 8 will give us minus 10 tj. Now to make it in this format, well, you can see that they just factorize in terms of i's and j's. So in terms of i's, you've got 8i and 5ti. So this combine these two, you get 8 plus 5ti. So yeah, I guess we've already shown this. I don't necessarily need to represent it here, but just for clarity. And then to make this expression, it's just 6j take away 10tj. And that factorizes out to me 6 minus 10tj. So in a way, when you can prove this one, then you can feel confident that you got B and C both right. So that's easy, 5 marks in the bag. Now the final part, D. This is the main bulk of the question. So find the values of T when the ships are 10 kilometers apart. Okay, now this is talking about the distance, right? So right now, you can think of this one as a displacement. So this is a vector. But this is also the distance if you took the magnitude of this value of this vector. So what I mean by that, we need to use Pythagoras now. Okay, this is actually quite a standard one. So we can say first things first. To find the magnitude of QP, this is the distance. We just have to take the square of each of these values and square root the whole thing. So it's basically going to be 8 plus 5t squared plus 6 minus 10t squared. And then square rooting it. And that's it. And the distance will basically be everything equal to 10. So this is now a distance value, so this equals 10. So you just go ahead and solve. So I'm going to go ahead and do it now, yeah? So just to get rid of the square root, I'm going to square both sides, so that disappears and this becomes 10 squared, so that becomes now 100 equals. So just need a little breather. So now we just have to expand these double brackets. So this is more or less a quadratic expression. So be careful. Remember, 8 plus 5t is just 8 plus 5t times 8 plus 5t. So we need 4 terms. And you can reduce it to make 3. So let's go ahead and expand in our own time. So we've got 8 times 8 is 64. 8 times 5 is 40t. Plus another 40t, you get 80t there. And then we get 5t times 5t is 25t squared. And then repeat the same here. You should get 36. 6 times minus 10 is minus 60. And another minus 60 is minus 120t. And then minus 10 squared is plus 100t squared. Alright, not bad so far. So now we just collect like terms. So let's just do it on this right side, yeah, just to make more space. So we can say therefore, just to make 100, let's make in terms of t squares, yeah. So combine the like terms, so you got 25t squared and 100t squared. That becomes 125t squared. In terms of t, we got 80 and minus 120. That becomes minus 40t. Oh, now here comes the numbers. 64 plus 36 is 100. Take away 100. Oh, that's beautiful. Now equals 0. So that's plus 0. So that all of this will be set to 0. And now we just find the values of t. So just factorize t out. So that's good. So I thought we were going to do quadratics, and I'm kind of glad we're not doing that. So it'll be 125t minus 40. So I hope you guys are following so far. So this means t could be 0. So basically when t is 0, the ship's at 10 kilometers apart, or this solution, so 125t minus 40 equals 0. So 125t equals 40, and t equals 40 over 125. And that is equivalent to, probably one is a decimal, 0.32. So t is 0.32. And to convert that to hours, just times it by 60. No. So this is 0. To convert to minutes to make sense of it. So this is basically 19.2 minutes. So basically when the ships are 10 kilometers apart, this happens at time 0 and time 0.32 hours. And that's it, guys. Hope this helps, and let me know what you guys get, and we can compare solutions. Otherwise, I shall see you lot soon. Ciao. Question 8. So this is the final problem of the paper. And this looks like a two-particle pulley problem, so let's check it out. Now, according to the information below, we have two particles A and B that have masses 2m and m respectively. So this means that A, we have a weight of 2m times g, so 2mg, and here mg. Okay. Now the particles are attached to the ends of a light inextensible string. Now since this is a string, we can assume that there's tension coming off it. So let's put T there and T there, and it's the same string, so tension should be the same for both really. Now what else we know? Particle A is held at rest on a fixed rough horizontal table at a distance d from a smooth light pulley. So first things first, this is a rough table, so we have to assume that there's some frictional force coming off it. So we can call the force coming off it F, but let's see which way it's going. Just by the shape of this, I'm just going to assume that the particle B will drop, but let's keep reading first. Okay, so on. So the coefficient of friction between A and the table is mu, okay, as usual, where mu is less than half. The string is parallel to the table from A to P, so that looks quite clear as well. And pass over the pulley. Okay, so carrying on where we left off. So just to make it quick, particle B hangs freely at rest vertically below P with the string taut and at a height h. So taut just means that the string is completely straight, it's tight more or less. So as B moves, A will move freely. If the string was slack, meaning it's loose, then there's no tension in the string. So think of taut as there being some effect to the string and a particle, so it has a tension. And yeah, the rest of it seems quite obvious. Okay, now here we go. So particle A is released from rest with the string taut and slides along the table. So this means that the direction of motion, let's call it A, and I'm going to change the color, is going this way. So here's A, meaning B is going to fall down towards the bottom. So, alright, not bad. So this seems okay so far. So this is the pressure. Since the weight is heavier here than here, if we let go of A, then B will just drop, and meaning A will drag along as B goes. So they're moving at the same constant acceleration, and technically the same speed until B hits the table, until it hits the floor, I mean. So, alright, so we're good now. Oh yeah, also the frictional force is backwards because, well, it's dragging along, and the frictional force is always, the direction of motion is always away from the acceleration, so it's always pulling back as you're dragging. And yeah, I think we're good now. So how about we go ahead and resolve this, yeah? Oh yeah, let's add a reaction force, why not? So A and B, so write down equations of motions for A and B, and then show that until B hits the floor, the acceleration A is g over 3, 1 minus 2 mu. Let's go ahead and do all of this, yeah? I think we have enough space to do here actually. So let's write equation of motion. So at A, we can do it here. So at A, what do we have? Let's have a think. So if we're going to resolve, let's resolve vertically, yeah? And because it's vertical, the acceleration is moving horizontal, so it's perpendicular to acceleration, so there's no acceleration. So B R must equal 2mg. Now if we resolve across towards direction of acceleration, so towards this way, we should have T minus F, and this must equal mass times acceleration, so 2m times A. Alright, I think that's all we can do from here then, and we already know what F is. F is also equivalent to mu R, and mu seems to be fixed, by the way, according to the text. So it looks like we're going to have a solution in terms of mu as given by here. Now let's look at the second equation for B, yeah? So at B, what do we have? If we follow the direction of motion of A, so that is going downwards, we can say that we have mg minus the tension, and this should equal mass times acceleration. Perfect. Now that's done. That's the easy 4 marks. The main bulk comes from finding an expression for B, which is that. So let's do that, yeah? So straight away, what we could do is, firstly, my personal advice is to eliminate tension and make acceleration subject over here. So for the second equation, if I make T the subject, by plussing t and minusing ma, we should have t equals mg minus ma. Okay, and now we can substitute this back into this equation. So now what we're going to have? We're going to have t replaces to be mg minus ma, f replaces to be mu r, so it'll be mu times 2mg, and this must all equal 2ma. So the dot here means just multiplying, yeah? And what can we do from here? Well, I would personally collect like terms, and actually first I'll cancel the m's, because every single term has an m, so this goes, this, and this. And now plussing a across and simplifying the rest, we should have g minus, what do we have? 2 mu g should equal 3a. Okay, so that's just some quick algebra. So plus a across, that becomes 3a, and collect terms. And now to make a the subject, well, just divide it by 3 and then factorize g out. So we should clearly have the solution. So we're going to have now a equals, firstly, factorizing g, so we're going to have 1 minus 2 mu. So it'll be g over 3, 1 minus 2 mu, just like they wanted. Okay, let's look at part C now, yeah? So find in terms of g, h, and mu, the speed of A at the instant when B hits the floor. So all this is effectively saying is find the speed, because we know the string is tall, A and B is moving at the same time. So this means effectively as B hits the ground, the speed of B as it hits the ground will be the exact same as the speed of A as it moves. So A would probably be somewhere here, traveling at a distance of h, and this will be its final speed. Remember, the particle is released from rest, so the initial speed was 0. So technically, the initial speed of v was also 0. So it's actually identical. As soon as b moves, a moves. When it hits the ground, well, I'm guessing the string might become slack, possibly. Now, what do we know? So we know that the initial speed is 0, the final speed is v, and the distance traveled is h. And we also have a constant acceleration, thanks to part b. So let's write all of this down below here, yeah? So we have acceleration given to be this. We also know that the distance is h. The initial speed u, not mu, u I mean, is 0, and the final speed is something we're trying to obtain. Now, what SUVAT equation can we use with S, A, U, and V? Okay, so just having a careful think about this. The most relatable equation I can think of would be the v squared minus u squared equals 2as. And I believe this is the perfect one. So let's go ahead and use that, yeah? Okay, so what do we have? So we can say straight away that plugging everything in, we can have v squared equals, and now plus u squared across. We're going to have 0 squared, that cancels out. So 2as. It will just be 2 times g over 3 times s. So it'll be, so 2 times h, so it'll be 2 times s, so 2 times h, so it'll be 2h, and then we have 2hg over 3, 1 minus 2 mu. I think that's it. Oh yeah, and then to find v, just square root that. So v equals the square root of, well, all of this. Yep, looks good to me. Okay, let's finish this off now. So the final two parts. So after particle B hits the floor, particle A continues to slide along the table. Now, given that mu equals a third and that A eventually comes to rest at the pulley, find D in terms of H. So this actually give us a lot of information here. So at this point, what we're trying to effectively say is that A comes to rest at this pulley here. So this would be the final resting point. So let me change the color so it doesn't mix up the rest of the diagram. So here's the final resting point. And now notice how when B hits the ground, well, we don't know if it's still bouncing or not, but I don't think it really matters. The whole point is that the string is now slack. So when something is slack, it means the tension in this case is useless. There's no more effect, so it's technically 0. So what we could do is firstly rework out the acceleration, because now we know that the particle is slowing down. It means there's a deceleration, so we need to find a negative acceleration. So let's resolve again with this new diagram. So I'm going to redraw it underneath here. So this would be in the original particle. We had a mass of 2mg here. We initially had a tension T, but now it's 0, so it's gone. So we can even rub this out completely. We still got the frictional force behind it because, well, you're on a rough ground. Okay, so that's the frictional force. Just make it look neat. And we still got the reaction, which is R. So everything is the same. R is still equivalent to 2mg. F is still mu r, which is technically 2mg mu. Okay. The only difference is, so now it's traveled along some distance. The distance is actually traveled here is from here to here. And the question wants us specifically to find d in terms of h. Is there the difference here? So what is the remaining the distance here? Well, he's already traveled h across, and he's still got d minus h left. So just because if you think about it, h plus d minus h gives us the total d. Yeah, so that's what it is. So that's our new distance. So let's put that there. So it's going to travel distance of d minus h across, and it's eventually going to reach over here, and that's when the speed will be 0. And this is some point. So let's call this point here firstly c. Yeah? So it's currently at c thanks to the instant when it hits the ground, and the speed of here is the same speed it was at b. So speed of a, what did we say it was? We said this was the speed, yeah. So let's call this the speed at c now. So this is the speed here, vc. All right, so it looks like we have pretty much everything. And just to recap what we're trying to find again, we're just trying to find the distance, and we need a new acceleration. Okay, so on recalculating the acceleration now, let's do it. Yeah, so acceleration now, new acceleration. So we can say firstly resolving this one, we had this. Now resolving towards the direction of motion this way, we should have firstly only minus f, and this should equal 2ma. And yeah, is that what they want in terms of m as well? So f we said was a 2mg mu, so it would be minus 2mg mu equals 2ma. The 2m both cancel out, so you're left with minus g mu equals a. So the acceleration is simply the gravitational potential times mu. Gravitational potential. It's just minus g times mu. Sorry guys, just feeling a bit tired. I've just been recording all day. So let's label everything. So that is the new acceleration. So now we have acceleration check, the distance s check, the initial speed vc check, and the final speed 0. Perfect. Let's do this. So I'll write it again here. So this was d minus h. Initial speed was vc, which is all of that. 2hg over 3. 2hg over 3. God, how can I forget? 1 minus 2 mu. Square rooted. And we also have the final speed, which is 0. So now at this stage, we can just repeat the same formula as we did previously using the v squared minus u squared equals 2as. Why? Because we have all the necessary variables. So let's do that. So using this and plugging everything back in, so v is 0. So v 0 minus u squared will just be the square of all of this, which is just simply 2hg over 3 times 1 minus 2 mu. And now we got 2as. So let's have a look. So 2 times a is minus 2g mu and s. So it'll just be minus 2g mu times d minus h, which is s. Right. Okay, so it looks like we're going to do a bit of manipulation, because the objective of this is to firstly make d the subject. It looks like we're going to have to eliminate, everything will be eliminated. So let's have a look. First things first, looking at both equations, g will be eliminated. We can just cross it out, because they both multiply to itself. The negative signs can cancel out. 2 can cancel out. Yeah, I think that's it for now. So let's expand. So we're going to have, on the left side, expand the bracket, h over 3 minus 2 mu over 3 h, I can't forget that, equals, and then here we're going to have was just mu, so it'll be mu d minus mu h. Okay. Oh yeah, we also know, I forgot, mu is also 1 over 3, yeah? That actually helps a lot. So given that mu is 1 over 3, you know, let me just help you. Let me just expand this right now. So if mu is 1 over 3, we're going to have h over 3 minus, let's see, 2 times 1 over 3 over 3. So all that becomes 2h over 9 equals, this becomes 1/3 of d minus 1/3 of h. Alright, now collecting like terms for h, so we're going to have h over 3 minus, so 1/3 minus 2/9 plus 1/3. So 1 over 3. Bear me a second, I'm actually writing all this down. That's 1 over 3. You should get, double checking. Let me just see that again. You should get 4/9, so 4/9 of h, and this should equal 1/3 of d. Now, we have to make, just recall, make d the subject, so simply just divide 1/3 across. So be answer divided by 1 over 3, 4/3, and that's it. D equals 4/3 of h. And yeah, makes sense. D has to be a bigger value because h is just a small quantity. And I believe that's it. And now for the final statement, describe what would happen if mu is half. Well, if mu is half, let's just see what happens. Just look at this VC for a second. If you substitute mu is half here, you'll get 1 minus 2 times a half. That will equate to 0. So you can effectively have 0 times this quantity, which will be 0, meaning the speed at this point was 0, meaning it's never reached this point. If you put 0 for the very beginning, you're going to get again 0. So what would really happen, you're going to have an equation with zeros. And you're going to have no acceleration and effectively no speed. So technically the particle of A will not move. B, then therefore B will also not move. So nothing moves. It's in something known as limiting equilibrium. And that's it, guys. I hope this all helps.